Welcome back to our discussion on atmospheric dynamics, and we're working our way through balanced flow. We finished with geostrophic wind and gradient wind. We talked about Rossby number. And now we're going to look at another type of balanced flow, which is the friction layer wind. So the friction layer wind is any wind that's influenced by friction from the surface. And we got to define the layers of the atmosphere, the lowest layers of the atmosphere, and there's one that's very close to the ground that goes up, well, about 3,000 or so feet. It's called the boundary layer. And the boundary layer, of course, is the lowest layer of the Earth's atmosphere. It goes up to about 3,000 feet from the Earth's surface. And this is where the wind is most influenced by friction from the Earth's surface and anything else that's sticking up above the Earth's surface. So if we had to break up the atmosphere, you'd break it up into the layer that's closest to the ground. We call that the boundary layer. And then the layer above that is your free atmosphere. Now the boundary layer can be broken up into other layers also, and one of those other layers is called the friction layer. And this layer is a thin layer of the atmosphere right adjacent to the Earth's surface. And it results in the wind slowing down to about anywhere from 1,500 to 3,000 feet above the ground. And above that, you have the free atmosphere, and the wind is blowing parallel to the isobars. So if we had to break up the boundary layer is kind of everything from the surface up to about 3,000. And then there's two other layers. We just talked about the friction layer. The friction layer goes from about anemometer level, which is about 30 feet, up to about 3,000 feet. Now that anemometer level actually kind of goes up a little bit higher, maybe anywhere up to about maybe 100 feet or so. So we're going to look at the friction layer wind and also the surface layer wind. First, let's start out with the surface layer wind. In the surface layer, right next to the surface of the Earth, of course, molecules of air are slowed down because they're sticking to the Earth's surface. We call that viscosity. It's just like oil. Oil is very viscous. So is molasses. And what that means is that molecules tend to attract to each other. So in this case, the air molecules are attracted to the surface of the Earth, and they actually stick to the surface of the Earth. So right at the molecular level, there's no wind moving right at the surface. But as you move up through the atmosphere, we're talking just a few inches above the ground, the wind is moving. The molecules are moving along. And there is some attraction between the molecules that are moving along and the molecules that are stuck to the surface of the Earth. So as a result, you have slower moving molecules. They're moving, but they're moving slower. And with each successive layer of molecules up higher and higher, they keep moving faster and faster as they move away from the surface of the Earth. So in the lowest layers of the atmosphere, the lowest 30 feet, maybe up to 100 feet or so, the wind increases exponentially with height. This is your surface layer wind. It does not change direction, it just increases in magnitude or in speed. So that's the surface layer. Now let's take a look at the next layer of the boundary layer, and that's your friction layer. Friction layer, as we said, goes from about the anemometer level up to about 3,000 feet. And in this layer, you'll notice that the winds turn clockwise with height. Down low, the winds are blowing across the isobars in towards low pressure. And then at the top of this layer, the winds are flowing parallel to the isobars. So this is what it would look like on a weather chart if you're looking at the surface station winds and the winds at 2,000 or 3,000 feet above the ground. The winds turn clockwise with height. So if we plotted these winds on a hodograph, we can actually see how they change with height. What is a hodograph? A hodograph is a way of representing the wind vectors. So you remember wind vectors, we like to draw on weather charts wind barbs, but vectors are actually point the direction that the wind is going towards. So if the wind's from the south, it's pointing towards the north. So let's use that. In our previous example, we saw winds that were blowing across the isobars. So They were blowing kind of southerly, so let's plot that, and the winds were only about 10 knots. And then up at 3,000 feet, they were blowing from the southwest, and they're blowing a little bit stronger, about 30 knots. So we can plot all the winds in the lowest layers of the atmosphere, and you'll notice that they keep changing kind of more and more westerly. They start out near the surface, about 30 feet above the ground. They're out of the south. Then they start switching around to the southwest, and finally they're out of the west-southwest at 3,000 feet, and they're stronger. So if you connect all of the points on this, all the wind vector heads, you'll get something that looks like this. And you can see that the winds kind of spiral as they go up through the atmosphere. This is, or was discovered by a scientist, an oceanographer actually, at the beginning of the 20th century. And they named this changing of wind with height, this spiral, after him. They call it the Ekman spiral. So that's a little bit about the winds in the friction layer and also in the surface layer. We're going to continue on and look at a mathematical description of what's going on with these winds, and then examine the forces that are acting on the wind.